Hey everybody, this is Mike Bartles from the Hydrologic Engineering Center. This lecture is part 4 within a series of lectures that are devoted to parametric modeling from a hydrologic and hydraulic modeling perspective. Within this video, we'll discuss how to compare a fitted model against data and verify its appropriateness. By the end of this lecture, you should be familiar with multiple ways to visualize the results of a model and compare them against observed data. I'll also present several qualitative visualizations and quantitative goodness of fit tools. Let's begin by revisiting the steps that are needed to perform a parametric modeling exercise or fit an analytical distribution. Within this lecture, we're going to focus on step 4. Step 4 emphasizes verifying that the model is appropriate for use with the data in question. There are multiple ways in which the model and data can be visualized together in order to form a qualitative comparison. This includes things like visualizing the model against the plotting positions of the data, as shown to the right. This is perhaps the most commonly used visualization tool within water resources applications. This type of plot can provide a quick means to weed out bad models. For instance, both of the models visualized here are probably not good choices to represent this data because the tail behavior of both don't adequately represent the data, which is usually where we're most interested in obtaining estimates. However, there are other ways to visualize the data which we'll describe on the next few slides. Also, there are numerous quantitative tests called goodness of fit tests that can be used to ascertain the appropriateness of the model. Instead of relying on just a single visualization or quantitative test, all should be used to justify the selection of a model. Plotting the observed data against the model on a cumulative distribution function, or CDF plot, and probability density function, or PDF plot, can provide valuable insight to the goodness of fit provided by the model. In the plots shown here, the same model is fit to the same data within a CDF and PDF plot. Also, the same number of bins and bin sizes are used in both plots. The model appears to fit the data much better within the CDF plot than the PDF plot, but how much of that visual cue is based upon the chosen bin size in the PDF plot? Perhaps less bins would allow better visualization of the model fit within the PDF plot. You can use different numbers of bins and/or bin sizes when visualizing the data in this way. Probability, or PP plots compare the probability of the data using the chosen plotting position formula against the inferred probability of the model. Quantile, or QQ plots compare the values of the actual data against the inferred value as predicted by the model. Both plots are valuable for comparing trends. However, the QQ plot is better at visualizing the tail behavior, while the PP plot is better at visualizing and comparing the center of the data. In both plots, solid black lines of perfect agreement are included for comparison. Now let's talk about quantitative goodness of fit tests. First up is the Kolmogorov-Smirnov, or KS test. This test is probably the most commonly used goodness of fit test in water resources applications because it's simple and non-parametric in that it doesn't rely upon the assumption of an underlying distribution. The KS test measures the largest difference in the CDF between the model and the observed data. In the example on the right, the largest difference between the CDF of the model and observed data is approximately 0.05. Therefore, the KS test statistic in this case would be 0.05. The Pearson chi-square test, which is often shortened to just chi-square, compares the entire model and distribution of data, not just the maximum in the CDF. It essentially asks, is there a significant difference between the model predicted frequencies and the frequencies within the observed data? This test first ranks the data, then places the values within bins. Within HEC SSB's implementation of this test, exactly 5 values are placed in each and every bin. This can result in the use of bins that are not uniform in size. Values cannot be shared within bins. Every possible value is in exactly one and only one bin. Finally, the first bin edge has a CDF value equal to 0, and the last bin has a CDF value equal to 1. Once the bins are created, this test statistic is computed using the sum of squared residuals between the model and data across the entire probability range. In the figure above, only a few bins are compared with red arrows, but all bins are compared. The name chi-square test arises from the fact that when the number of sampled elements in each bin is equivalent to the expected value, it is predicted by the chi-square distribution with n-1 degrees of freedom. Now there are many goodness of fit tests that have been developed for different types of data, distributions, and fitting methods. I'll briefly describe 3 additional tests that are available within HECSSP. This list is by no means exhaustive, as everybody and their brother has a goodness of fit test. The Anderson-Darling test assesses whether a sample comes from a selected distribution. This test works by first assuming that the data does arise from the chosen distribution, and then tests the data for uniformity with a simple distance test. Bayesian Information Criterion, or BIC, and Akaike Information Criterion, or AIC, are similar tests. Both the BIC and AIC tests make use of likelihood functions, which were briefly introduced in the last lecture for use within the maximum likelihood estimation fitting method. This means that these tests aren't appropriate for use when fitting methods like method of moments are used, which limits their applicability. However, these tests are really cool in that they penalize complex models in an attempt to weed out overfitting. In this case, model complexity refers to the number of parameters. So if you use a 3-parameter model like log Pearson type 3, it'll be penalized more than a 2-parameter model like log normal. In this video, we talked about the visualization of model results against observed data. Several qualitative visualization tools were presented in addition to several quantitative goodness of fit tests. Remember that when you ascertain whether your chosen model is appropriate for use, your judgment shouldn't be based upon a single visualization or quantitative test. Instead, you should use all of the tools that are available. The next lecture will discuss various sources of uncertainty in your results and how to combine different models together. Thanks for watching, and I'll see you in the next one.